Kinematics in one dimension. Kinematics deals with concepts used to describe the motion. For example, how we describe the speed of an moving object, how we describe the motion of an object on a rough surface. So any concept we use to describe the motion, we consider or it falls under kinematics. And one dimension is motion of an object along a straight line, or it can be vertical, it can be horizontal, or it can be any arbitrary direction. Motion of an object, any arbitrary straight line, uh, uh, we consider in this chapter. Yesterday, uh, unfortunately, we couldn't do the class well, but I will try to resend a new audio clip with the yesterday class. That class mainly we talk about scalars and vectors. Scalars are quantities which has no direction. For example, distance. Distance is a scalar, a quantity which doesn't have a direction. It can be 5 meters, 10 kilograms. Its mass is just a quantity which it has a magnitude but no direction. For example, on the other hand, vectors which has a magnitude and also a direction. So displacement is a such a quantity, has a magnitude and a direction. Here is the origin, which is, we can call it, it's a zero position. And front side of the car is at x naught position. We call it initial position. And this clock shows the time t equals 0. 0 always most of the time we use for origin or initial started position. And after some time interval t, the front side of the car is at position x. The change of this distance, initial position to the final position, we call it delta x. Delta means a change. X means position along x direction. Change of position along x direction, we call it position delta x, and which is equal to x minus x naught. So as you see, it's bold letters with an arrow on top. So which means those are vectors. We usually use bold letters or letters with arrows. There are a couple of different way of writing a vector. Sometimes just bold letter or bold letter with an arrow in this case, or just a letter with arrow on top. So there are so many different notations we use to describe the vector. So this is a one dimension, therefore particularly x direction. So the delta x, position change along x direction, is equal to x minus x naught. We call it displacement, and the unit of displacement is meters, and the direction is the direction from final location to initial position. Okay, let me do another example. Let me split this line into a couple of different sections. Like, let's say this is five meters, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 meters. Now let's consider an object sitting at this position. This is the initial position. Initial position. And we call it x naught, and which is equal to 10, 11, 12, 13, 13 meters. And let's say time, initial time, t naught is 5 seconds. Okay. After some time interval, this object moves to this location. Now it's here. This is your final position. And your x is a vector equals 6 meters, and time let's say 12 seconds. If I ask you to calculate the displacement, which is delta x, which is equal to x final position minus initial position. Okay, so all this needs to have bars on top, which indicates it's a vector. So initial position is 13 meters and final position is 6. So this is your final, this is your initial. Okay, so final is 6 meters minus initial position is 13 meters, which is equal to negative 7. Meters. So this negative sign represents the direction. We know delta x is a vector, therefore it has a magnitude which is 7. In addition, it has to have a direction, delta x. It has to have a direction which is to your left. So if you want, you can write magnitude, which is equal to 7 meters to west. Or 7 meters to left. Either way is fine, you know. So as far as if you have negative sign or if you have a direction with the magnitude, we know that it's a vector which has a magnitude and a direction. Our next topic is average speed, which defined as distance over time. Uh, Let me take an example and explain you what this means. Let me consider a straight line, and we have a object rolling along this straight line with a initial with a speed of 50 miles per hour. At some point, another point, 60 miles per hour, and at point B, 55 miles per hour. And let's say the distance between A and B is let's say 150 miles, 150 miles, and it took time 3 hours to travel from A to B. So if you use the previous equation to calculate the average speed, you come up with 150 miles divided by the time, 3 hours. So your answer is 50 miles per hour. As you see, from A to B, you cannot tell exactly what is your speed going to be between A and B. If you know the distance from A to B and the time it took to travel from A to B, you can talk about average speed. It took 50 miles. You drive in like 50 miles per hour from A to B. But in reality, real situation, you sometimes you drive like 50, sometimes 30 miles per hour, sometimes 60 miles per hour. So from A to B, your depending on the location, your speed can change. But when we talk speed, you have to talk about average speed, because you cannot tell exactly what is your speed going to be at a given time. If you're going to talk about specific speeds at a given location, for example, at A, your speed is 50 miles per hour. At point B, 55 miles per hour. If you just talking about the speeds at a given point, then that speed, let's say at point B, your speed is 55 miles per hour. Then you call this speed instantaneous speed. Instantaneous speed, which is your speed at a given location at a given time. At that instant, you can tell your speed. which is called instantaneous, but most of the time we talk about average speed, which is a average speed over a certain period of time or a certain distance. Here's one of examples in your textbook. Average speed is distance over time. So this equation has three unknowns or variables. One is average speed, distance, or time. So speed, distance, time. If you know two of them, any two, you can calculate the remaining one. For this example, it has given the distance and the speed. So you have given distance and speed and asked to calculate the time. So if you want to calculate the time, you're going to rearrange this equation. I'm sorry, it's given time and speed. You have time and speed, and you have to calculate the distance. So if you want to calculate distance, you need to rearrange this equation or solve for this equation, distance, which is equals to time times speed. So time is 1.5 hours and speed is 2.22 meters per second. So now you notice the given the units, meters per second for speed, and the time is in hours. So if you have hours and meters per second, you know seconds also unit of time. So if you have hours, you need to convert hours to seconds so that you have same units for both quantities they have given in this problem. So when you do this, you can cancel seconds to seconds and you left with one unit, which is meters. When you calculate, your distance is 2.22 times 5400. Seconds to seconds cancel, you left with meters. Meters is units for distance. So by looking at the units, you can tell your final answer is correct because you have the right units. Our next topic is average velocity, which is equal to displacement over time. In slide number 3, we talk about the difference between scalars and vectors, and we talk about distance and the displacement. The difference between distance and displacement is distance is a scalar quantity which has a magnitude but no direction. Displacement is a special case of distance which has a magnitude. In addition, it has a particular direction. And the next we learn about speed, which is distance over time. And again, distance doesn't have a direction, therefore speed is related to distance and time, therefore speed doesn't have a direction. Now the new topic is our velocity. Velocity is displacement over time. Velocity also belongs to vector category because velocity associated with displacement and time. Since the displacement has units, direction, velocity also has a particular direction. Therefore, velocity also become a vector. Okay, here's an example in your textbook. There are two cases here. It moves from left to right and then right to left. So we have to consider both occasions if you want to calculate the average velocity. So let's consider case A. The car moves from left to right. Starting position is t equals 0 and the end finish location, the time is 4.740 and the distance is plus 1609 meters. Plus means it's moved to right direction or east, which is a plus, and if it travels in the opposite direction as in B, you will see a negative sign, which means it travels to the left or west direction. So if you calculate the average velocity for the case A, you will have to write delta x, uh, final position minus initial position, which is plus 1609 divided by the time interval, and you will end up getting a plus number, which is you have a positive velocity, which is you traveling along positive x direction, positive x direction. And in B, you have a negative number because you travel opposite to positive x direction. Therefore, you have your displacement is a negative number. Therefore, your final velocity also a negative number. Instantaneous velocity. A couple of slides ago, I talked about when I explain speed, average speed, I draw a small sketch and show that when an object moves along a straight line, different locations at a different particular time at a given location, you have a specific speed, and that specific speed you call it instantaneous speed. And when you travel on a straight line, you talk about a direction as well in addition to the speed. Therefore, you can say it's instantaneous velocity. At that particular location, particular time, you have a specific velocity or speed. Speed is you don't have a direction, but if you travel on a straight line, you call it velocity because you have a speed with a particular direction and given moment at very small time interval, you get, that's why delta t goes to 0, which is very small time interval, which considers a one location or one point. Your average velocity becomes instantaneous velocity. For example, when you're driving in your car, when you look up your speedometer, you will see your speed, which means that speed is your speed of the car at that given location. If you go in on a straight line or racetrack, straight line, that speed you can consider as your instantaneous velocity at a given location at a specific time. You call it instantaneous velocity. Our next topic is average acceleration. Acceleration is defined as velocity change divided by the time. We use letter A for acceleration, V for velocity, X for position or displacement, and for acceleration, average acceleration A bar is equal to final velocity minus initial velocity divided by final time minus initial time, which is equal to velocity change over delta means change of v, change of velocity divided by delta t, change of time. So this is final. So initial. So acceleration A is equal to final velocity minus initial. Note means initial or start divided by final time minus initial time. Okay, I'm adding things to this list, scalars and vectors. We start with distance and displacement, and then we add speed and velocity. And now I add new one, acceleration, change of velocity divided by change of time. Now you might ask, can't we find a corresponding acceleration or another term for scalars. We can talk about in chapter 4th or 5th when we talk about circular rotational motion, because when you take an object moving with constant speed or constant speed, your speed is same but your direction is changing, so which means you have a particular velocity at a particular direction at every point, and if you change the velocity you will have acceleration. So we can talk about that in a separate section. Let me skip these examples and I can come back to these examples, so I can do some different examples after this chapter, and let me move to slide number 24. So far we learned a couple of equations, actually three equations. Displacement delta x equals x minus x naught, final position minus initial position, and velocity v, x minus x naught divided by time difference t minus t naught, and acceleration, the last one we learn, final velocity minus initial velocity divided by final time minus initial time. So from now on I'm going to write v equals x minus x naught divided by t minus t naught. It's because of the simplicity, because it's hard to write or draw arrows and bold letters. So simplicity, we write v equals x minus x naught and t minus t naught without any arrows or bold letters, but it means v, x and x naught are vectors. Okay, so let's consider the same equation. Average velocity equals x minus x naught, t minus t naught. X naught and t naught are initial time and initial position. Let's assume initial time and initial position is 0. You always consider, when you use a stopwatch, you can make it 0 and you can consider that as your initial time, and also you can start measuring the distance from position point 0. And when you make x naught and t naught 0, you don't have these two in your equation anymore, so you end up with v equals x over t. So you can rearrange this equation. X is equal to v times t. You just cross multiply, and average velocity v bar is equal to initial velocity plus final velocity divided by 2. So it's average, final minus initial divided by 2 times t. So we have a equation now. Final position equals half times initial velocity plus final velocity and time it took. And also we can make a little bit modification to this equation. We learn acceleration is velocity change over time difference, and we can consider initial time is 0, but we cannot consider always as initial speed is 0. Therefore we have to keep initial velocity as a certain number. So if I consider initial time is 0, then you have a equals v minus v naught over t, and if you rearrange this equation a little bit, a times t is equal to v minus v naught, and if you rearrange this equation a little bit more, you can write v equals v naught plus at. This is your second equation. We just talk about equation for x, average position, final position, which is half v naught initial velocity plus final velocity times t. And now we learn another second equation. Final velocity is equal to initial velocity plus acceleration is a. Acceleration times time. When we work on these kinematic problems, you always come across x, which is position. If you see x naught, which is position but initial position, and then a acceleration, v as its final velocity. If you see a naught with v, initial velocity, and t is time. So you have several equations combination of these variables. In the previous two chapters, two slides, we learned how to derive two equations. One for velocity, which is equal to v naught plus at, and then we learn another equation for final position. And now I'm going to combine these two equations and write a different equation. So let me use a different color. So x final position is equal to half times initial position plus final position times t. So instead of the final velocity here, I can substitute whole equation. So x is equal to half right here. This v naught is right here. And instead of this v, I can write v naught plus at right here. And then we can add v naught to v. Let me write another line, which is equal to half in parentheses v naught plus v become 2 v naught plus a t times t. Now I can get rid of parentheses by multiplying half and t. Then I have half times 2 v naught, and there's a t here, plus half at times t, a t square. So half cancel, therefore I have x equals v naught t half at square. That's the third equation. Let me move to slide number 33, which summarize all equations we learned. So in this class, I expect you to learn these equations and learn how to use these equations, these four equations. Basically, this equation, this, and actually all four. Most of the time you see these three, and sometimes you see x or final position equals half v naught plus v times t, but you have to work a lot with these three equations when you work on homework and other tests and labs in this class. Let me move to slide number 38. Okay, let's talk about free-falling bodies or free-falling objects. Free fall means anything falls onto the Earth's surface if there is no air resistance like wind or mainly wind. When they fall, we know it has velocity. When something falls from top of a building, for example, its initial velocity is zero because it just dropping from a ceiling or roof of a building. Initial speed, just after it drop, its initial speed is very much is zero, but by practice, if something keep falling, its velocity or speed keep increasing. So if there's a velocity change, we know we have acceleration. So in this particular case, anything falls onto the Earth's surface in the absence of air resistance. That's the main thing. In the absence of air resistance, we have acceleration, and that particular acceleration, we use a special name. We call it acceleration due to gravity, and we use J instead of A, and this number is exact number is 9.80 meters per second square, or 9.8 meters per second per second. So every second its speed increase by 9.8 meters. This is a demo I show in the class. Unfortunately, I can't show it, but this tube you can hook up to a vacuum pump, and when you hook up to the vacuum pump and make a vacuum inside, and there are two particles, one is like a piece of cotton, and also a very tiny piece of paper, and if you let this to drop from one end to the other end, you can see light object and the heavier object falls at the same speed. Every location, when it drop from top, you see it both objects at the same location. When it keep falling, both objects at the same level. So which means their speed, regardless of their weight, they fall at the same velocity. So if the velocity change increases, you can calculate the gravity or acceleration. That acceleration is 9.8 meters per second. On the other hand, if this tube filled with air, and when you let these two fall, you see, because of the wind resistance, this takes long time to drop. So therefore, we cannot consider this G is correct for this case. So free falling, this no longer a free falling scenario because it has air resistance. Okay, let me take an example, of a free falling object. At time t equals 0, seconds, its initial speed is 0. I will write t1, t2. So every position, time increase by 1 second. T2 2 seconds, T3, T4 5 seconds. So you can calculate the acceleration. between any two events. So if you consider these two, acceleration is v1 minus v0 divided by t1 minus t. 10 meters per second divided by 1. 10 meters per second or 10 meters per second square. Or if you consider these two cases, acceleration is final velocity, which is 40, and the velocity before that event is 30, and the time difference is 5 minus 3. I'm sorry, this is 4 seconds. So let me fix it. Four seconds. So 40 minus 30 is 10 meters per second, and 4 minus 3 is 1 meters per second. Your answer is 10 meters per second. So your acceleration, no matter any two events you consider, you have the same number as before. So acceleration due to gravity, any object falls under influence of the gravity has a constant value. We call it AG, acceleration due to gravity. More specifically, this is 9.8, but we approximate to meters per second or meters per second square. We can approximate to 10 because it's easy to work with multiples of 10. So most of the time when we work on examples, we use 10, but when you do the lab, you have to use 9.8.